Good morning and hello here from greetings from Cairo in Egypt. I'm pleased to be with you virtually today to present to you at the 10th International Conference on Instrumentation and Control Systems, the CICS 2022, that is held in Dubai, UAE. Unfortunately, I do have regrets that not presenting this research live at the conference in Dubai due to the COVID travel restrictions as well as for my military service. So I'll quickly present myself. My name is Shaher Ahmed. I'm a recent mechatronics engineering graduate from the German University in Cairo. I'm also currently in the process of pursuing a Master's of Science degree in mechatronics focused on industrial automation, wireless sensor networks and machine learning. On behalf of my teammates, Mohamed, Shekha, Suhaila, Skran, and Abdelrahman, Bassyouny, I'll be presenting this research to you. So as we've mentioned, the title of this research is the investigation of optimization techniques on the elevated dispatching problem. This research has been conducted by my teammates and I during our bachelor's degree at the TUC. So before I start, I just want to offer my sincere gratitude and thanks to my professor, Professor Dr. Ahmed Shaher, and as well as to engineers Catherine and Shayma for the knowledge that we've actually gained from them, as well as the lecture notes that they have provided in order to conduct this research. So as for the outline of this presentation, first we begin by introducing the elevated dispatching problem. Next, we discuss the problem statement on the formulation of the elevated dispatching problem. And this is also followed by the discussion of the methodology, where we give a quick overview on the algorithms that we've implemented, such as the genetic algorithm, the simulated annealing, the particle swarm optimization, and the whale optimization algorithm. We then move on to the results and discussion, and finally, we conclude this presentation with giving you a conclusion and the future recommendations of the authors. Now, to start with the introduction, our application of this presentation is a very common application that all of us use, which are the elevators. They are basically designed to transport the passengers from the initial floor or the current floor to their destinations more comfortably and efficiently. So the use of elevators have actually been increasing throughout the years since, more constructions actually has been happening. And as for the manufacturers of the elevators, an important concern for them is the efficiency of the elevators, as well as the reducing of the passenger waiting time, as well as the time that it takes the passengers to their destinations. Hence, this is why the elevated dispatching problem has actually become a very active research topic in both the academia and in the industry. It's actually a very good example of a stochastic optimal control problem of economic importance that is quite actually too large to be solved by classical techniques such as the dynamic programming. Now, I present to you a few details or a quick overview on the optimization techniques. So the definition of optimization is to quickly or to find an alternative with the most cost-effective or the highest achievable performance under some given constraints. And this is done by maximizing the desired factors that we'd want to maximize and minimizing undesired ones. Optimization actually has a lot of techniques such as deterministic and stochastic, and they actually also include numerical heuristics and meta-heuristics optimization techniques. They are categorized into two main techniques, which are the trajectory-based and the population-based. The meaning of trajectory is that the main difference between the two techniques is that in the trajectory-based technique, there is only one solution per iteration. However, in the population-based technique, there is more than one solution per iteration. As for the elements of optimization problem, in any optimization problem, you must define three elements or three parameters, which include the decision variables, the objective function, and the constraints function. So the decision variables are pretty much the variables which are needed to be found by the optimization algorithm. These variables are used to tune or are to be tuned by the algorithm itself in order to make difference between the solutions. The constraint function actually is the restrictions that must be satisfied in order to produce an acceptable design. And once the first and third elements are then satisfied, we then move on to the objective function, which is the criterion against the quality of the design is being assessed. So this is whether we know this solution is actually a good or a better solution. A very famous optimization problem is the traveling salesman problem. The traveling salesman problem is a very interesting problem that I do recommend the ones interested in the optimization field to actually further read on this topic. To quickly give you an overview about the traveling salesman problem, it's where a salesman is trying to visit a number of cities in a country, and his objective is to find the best route that the traveling salesman would take in order to travel between all of these cities with the minimal amount of distance that required. So the aim of this research, or the research gap, actually is the need for a comparative study to assess the optimality and efficiency of the elevated dispatching problem, and to compare it or to compute a dispatching scheme, which is the result of the algorithms that are being implemented in order to lower the average trip time for all of the passengers. Now with the second section, which is the problem statement on formulation. So as I've mentioned, the main objective of the elevated dispatching problem is actually to provide the passengers with the shortest waiting and the destination time. So this can actually be considered as a multi-objective optimization problem, meaning that we'd want to optimize two parameters, which are the shortest waiting and the time takes the passengers to the destination. However, those two parameters can actually be combined into one parameter, which is the journey time. So the objective overall is to minimize the average journey time of all of the passengers. We've actually built a case study, sorry, where we've where we have a building where it's actually serviced by one single elevator, and the floors we have 20 floors, 21 floors. 10 passengers, and the elevator is actually initially at the 4th floor. The decision variables of the elevator dispatching problem, in order to relate the problem with the elements of the optimization techniques that I've mentioned in the previous two slides, are the floor numbers that can actually be represented in an array that represents the route that the elevator would follow in order to reach the average journey time for all of the passengers. The constraints actually of this case study is the exclusion of the same floor calls from different passengers, meaning that no two passengers can have the same destination or current floor. The elevator dispatching problem is actually a permutation problem, meaning that the order of the solution is very important, because, as I mentioned, the order presents the route that the elevator will follow. So the solution is represented as an array containing the order of the floors that be taken by the elevator to drop off and pick up the passengers, performing the calls of each of the passengers. So to continue with the problem statement and formulation, in this slide, we deduced the equations needed in order to find an objective function. The model that we have presented should have some specific parameters that should be specified, such as the opening time, the time it takes the elevator to open the doors, and the closing time, the passenger's load time, the time that it actually takes the passengers to load their time, and the time between the floors. From these parameters and with the few equations, we've actually deduced equations 4 and 5. Equation 6 is the just the summation between equation 4 and 5. And 7 is the average journey time, or the objective function that we are trying to minimize. So it's just the summation of equation 6 of all of the passengers, and then we divide it by the number of passengers. Now on to the methodology sections. We just give you a quick overview over the algorithms that we've actually implemented using Python programming language. So for the simulated annealing, it's actually one of the most used heuristic approaches in the optimization techniques. It's inspired by the metal annealing process, hence the word annealing. So to quickly go over the, the pseudocode of the simulated annealing, we initialize an initial variable, a current temperature, and we initialize a final temperature as well as the maximum number of iterations that we'd want to require, the best variable or the best solution so far, and the best objective function. These two parameters are actually initialized as the x value, which is the first in the iteration. In this space, we have the iteration that we iterate over the number over this over these conditions, which are the current temperature. If the current temperature is greater than the final temperature, and if that the iteration or the current iteration is still less than the maximum number of iterations that we have defined here. So first, we begin by generating a new random feasible solutions. We compute the change of energy, change of E. This is actually the objective function that we've deduced in the previous slide. So if the change of energy is actually less than 0, this means that the solution is actually a better one. However, if it's less or it's greater than 0, in that case, we initialize a new variable, which is R. It's a random number between 0 and 1. And if it's less than P, which is the exponential function of the negative value of the change of energy divided by T. If this condition is actually true, we then accept the solution, and then we update the temperature cooling schedule in order to reduce the temperature. And then we update the iteration counter. And this conditions are then, if these conditions are not then satisfied, we then go outside of the loop and get the best solution from the simulated annealing algorithm. As for the genetic algorithms are actually randomized search algorithms designed to mimic the mechanics of natural selection and natural genetics. They are inspired by the human body or by humans, such as we have the word chromosomes, and they work on string structures, which is like biological structures that evolve over time according to the rule of survival and the fittest through a randomized yet organized information. So in every new generation, a new set of strings is actually being created using parts of the fittest members of the set. This is actually explained here in this loop, where we first initialize an X solution, first initialize a number of iterations, M, which is the number of chromosomes, meaning that per iteration, we don't have one solution, but we actually have M number of solutions, where in each solution, we have an elite member and a crossover members and mutate worst members. The elite member is actually the best solution from all of the chromosomes. The mutant is actually the worst, and the crossover is chosen by the Davis crossover method in the genetic algorithm, where we choose the best or the elite member as well as the second best elite member. So after we've generated the random number of solutions and we've picked our members, we then compute the fittest value, which is the objective function, to see which one is the elite and the crossover and the mutant for the next iteration. We update the iteration counter, and then we iterate until the conditions are not then satisfied. To quickly go over the particle swarm optimization and the next algorithm, which is the whale optimization algorithm. For the particle swarm and the whale, they are actually arithmetic problems, meaning that they don't deal with permutation problems. However, in order to make them usable on the elevated dispatching problem, we've actually used a space transformation in order to use these algorithms. To quickly go over the algorithm, they are actually arithmetic, so we just do some calculations or mathematical calculations here in this section, and then we just compute the fitness value, and then we iterate until the stopping criteria has not actually been met. This is for the particle swarm, and the same goes for the whale optimization algorithm. As we can see here, we are just using, or depending on the values that we have computed here in the conditions, here, here, and here, it depends if these conditions are satisfied or not. We use one of these calculations. to the ones interested in knowing the weight optimization algorithm and in the particle form optimization technique, I would refer you to our research paper, where we've actually explained the weight optimization algorithm and the particles form optimization technique quite well. As for the results, we've actually started this research by trial cases. They've actually been implemented on all of the 4 algorithms, where we've established 4 passengers and 8 floors. And the reason why we've actually established a trial case is to compare the results between the trial case and the case study of the research itself, see how the results the results of the parameters would differ with a smaller case. So as for the simulated annealing, the genetic algorithm, the PSO, and the weight, we can see on the convergence plot, which is the x-axis is the number of iterations, and the fitness value, which is the objective function, on the y-axis. We can see that with the high number of iterations, that the value of the objective function actually gets better. However, we can see that in the genetic algorithm, we have reached a value of 97.5 seconds per passenger, which means that the average passenger takes 97.5 seconds in order to reach the destination. This is, of course, in the trial case study, where we have 8 floors and 4 passengers. And the average objective or fitness value in the algorithms in 5 runs or the best is also in the genetic algorithm, where we have 110 seconds, and is then followed by the weight optimization, and then the simulated annealing, and then finally the PSO. But as for the case study of this research, we can see that this is our main case study, and we can see the convergence plot, also the x-axis, the number of iterations, and the fitness value, and we can see all of the algorithms being plotted on one chart. So as we can see here in the chart, it's observed that with the increased number of solutions, the solution converges to the best possible fitness value of the algorithm with respect to the case study itself. It's also observed during the case study or the trial case runs that with the more number of passengers, the more iterations are actually needed in order to reach an optimal solution, as there are several combinations of solutions possible. So you can see here in orange that the genetic algorithm actually performs best over the other algorithms, where it reaches a fitness value of 22.3 seconds. As for the simulated annealing, we can see that it's actually fluctuating between the fitness values. This is because the condition where I've mentioned where R is less than P, the exponential of negative the change of E over T. Because of this part of this equation, we actually sometimes accept solutions that are actually worse than the fitness value. However, for the PSO and the weight optimization algorithm, they actually perform very similarly, and it's actually expected that if the number of iterations increases, we would see that the algorithms would then get into a better solution. So the reason why these for the PSO and the weight optimization algorithm that are actually their fitness values are actually very far from the genetic algorithm is because of the space transformation that's being occurred on the PSO and the weight optimization algorithm. As we've mentioned, they are both arithmetic problems, and the elevator dispatching problem is actually a permutation problem. Now, to conclude this presentation, because of the large growth of buildings and the increased demand for more sophisticated elevators and the elevator dispatching systems, they're always being enhanced and they're always being evolving. And these upgraded methods that we have mentioned are actually designed to reduce the waiting time. So the current research work evaluates the usage of 4 optimization algorithms in order to provide a solution for the elevator dispatching problem. So the algorithms, the simulated annealing, the genetic algorithm, the particle swarm, and the weight optimization are also implemented in this research paper using Python programming language, and they are being tested on a test case in order to solve the elevator dispatching problem, in order to improve the efficiency and to provide a better user experience to evaluate the test evaluate the test and the performance of these 4 algorithms. We've computed 4 performance indices that are computed as the average and the optimal fitness values in 5 runs, and in order to consider which of the algorithms is actually best used in the industry. So based on the findings, we've found that the genetic algorithm performed better than other algorithms, as we have seen in the trial case and in the case study itself. So our future recommendation is actually to use the genetic algorithm in the practical and the dynamic dispatching scheme. We also highly recommend using adaptive optimization techniques. Further research is actually required to develop, implement, and evaluate the use of multiple elevators. This research paper, as I've mentioned, only considered the use of 1 single elevator. We advise that this study actually could be improved by the further collection of elevator traffic data over the course of a complete working day, where we run the algorithms at the different periods of the day and taking the average of the results. A limitation that could actually improve the study is the inclusion of the same floor calls from different passengers, which was actually the constraints of our problem. So once again, I would like to acknowledge and give thanks to our professor, Professor Omar Shekha, Engineer Jamal Bakrish, and Engineer Catherine at the Department of Mechatronics at the German University in Cairo, for the help and the usage of lecture notes that they have provided to us throughout the course of this project. Thank you.